out of the electrical force and into the related force, magnetic force. So this is the first little bit is a review, and then we get into some calculations, which we did not do in grade 11. So I guess the thing is with magnetic force is that if you have a magnetic field and you have something that's charged, it will experience a magnetic force. The example of that is an electric motor. Okay. So the reason for the force is that the moving charge will create its own field that will attract or oppose the field in which the charge is located. So we'll see some examples, but the motor principle, the left-hand rule for the motor principle, and we always talked in grade 11, I always did the left-hand rule. This year we'll talk about the right-hand rule more frequently, but we'll get there. If an electric current is moving in a magnetic field, a magnetic force will be generated such that the charged object will experience a force. Here's the left-hand rule. Your fingers point in the direction of the magnetic field, which by convention we say the magnetic field is south. Whatever the south pole is, that's the direction. Your thumb points in the direction of the current, and your palm will show you the direction of the force. And so this means nothing without actually doing it. So let's see. So first of all, I'll say this was some magnet, and that's my south pole, that's my north pole. And I've got, this is a conductor that's carrying electrons. That dot, you might remember from last year, it means that the electrons are coming sort of out of the page towards you, okay? So remember the circle here is like we're looking head on a conductor that's moving into the page, okay? So for the motor principle to work, you need a fixed magnet, and then you also need a conductor. And the idea is that this current in this conductor will create its own magnetic force, magnetic field, sorry. And then that magnetic field will interact with the field generated by this fixed magnet. And those two will either cause an attraction where this conductor will want to move up, or a repulsion where the conductor will want to move down. Oh yeah, here it is. Yep, so I told you this, that if you see a dot, that means electrons are flowing towards you, out of the page, and X means into the page. So if that's the picture you see, it means the electrons are flowing away from you and into your page. The other thing is to remember that the magnetic field around a conductor, a circular conductor like that cylindrical shaped conductor, will be concentric circles, and that's actually some picture someone took at some point of the iron filings. Okay, and so these little concentric circles, and the direction, you know, you don't need to remember all these rules exactly, but the direction of that magnetic field, so to speak, would be, you know, in this case, clockwise. And that's because your thumb follows the electrons and your fingers, this is your left hand, your thumb follows the electrons, so it would be out of the page, and your fingers would wrap around, and the arrows should point the same direction your fingers wrap around. Okay? In the fixed magnet, the field in a magnet always points south, and this is just a picture. You know, that's what iron filings would look like. And of course, iron filings don't have an arrow on them, right, to show you what direction they're pointing, but there is a definite direction to magnetic force fields. Okay? And so the idea behind the motor principle is that the magnetic field, those two magnetic fields interact with each other, okay, causing the conductor to feel a force. So, you know, what would happen is in this particular case, our magnetic field on the fixed magnet points south, and on the conductor is going in that clockwise fashion. And see, these two fields then are both in the same direction. So that's going to cause, you know, it's sort of a push down on the conductor, and sort of this field will bunch up. They're trying to get away from each other. Because just like electric charges, similar charges repel, similar magnetic fields, directions, similar poles, like north repels north. It's the same idea. Okay? So this thing will feel a force downward. And that's the motor principle. And we can just add some numbers to that now. Oh, this one's actually no numbers yet. So we're going to determine the direction of the magnetic force just using the left-hand rule. Okay? So remembering, so everything I told you about the direction of the field, that's all great, but is that the left-hand rule just makes it easier to remember it all. Flat palm, fingers point south, fixed south, and your thumb follows the electrons. So in this case, if you did that yourself, and your palm would tell you the direction of the force. So my fingers on my left hand point towards the red, to the south pole there. My thumb points out of the page with the electrons. My palm then is up, and so that up, therefore that's the direction of the force. Okay, we did all this last year. Okay, now here's the thing. Sometimes we deal with positive charges. I remember, you might remember in grade 11 me mentioning conventional current. Well, conventional current is more of an electrician's term, but the reality is that, in this course we don't talk as much about regular electric current through conductors. We talk more about moving charges. And sometimes, or just as frequently, they're positive. And if they are, you do everything the same, but with your right hand instead of your left hand. So the thumb follows the direction of the protons or the positively charged particles, or, your palm faces south still, that doesn't change. But now with your right hand, the only difference is your thumb follows the direction of the positively charged particle instead of the electric current. And that's only if it's a positive charge. So a positive charge, use your right hand. Negative charge, use your left hand. Okay, here's the equation for magnetic force. So Fm is the magnetic force. That's the symbol we give it, M, for magnetic force. Q is the charge. V is the speed, nothing new there. Angle between the motion and the magnetic field. We'll talk about that later. And B is something new. It's called magnetic field strength. Magnetic field strength is to magnetic force as electric field strength is to electric force, as gravitational field strength is to gravitational force. Okay? And it has a symbol, it has a unit, of T for Tesla. Okay? So that's the equation for magnetic force, which is easy if you know all those things, which often we do, actually. Excuse me. All right, so this magnetic field strength, though, the thing with magnetic field strength is not just due to, the presence of, the amount of force an object in a magnetic field experiences isn't only due to whatever magnet is causing the magnetic field. It's also, if it's a charged object, it's also related to its speed. Okay? We give it the unit Tesla. It's quite odd, and for now, don't worry about it too much. Hopefully you understand a bit more later, but T for Tesla, that's the big thing. But what it means is that if the field strength is 1 Tesla, then 1 coulomb of charge moving at 1 meter per second will have a force of 1 Newton, and that's, someone just made that up. Kind of like they just made up that gravitational potential energy is negative. They made that up so it works, and everybody uses it, and everything's okay. So this is just, it could have been, someone could have said 1 Tesla is 17 coulombs of charge moving at 11 meters per second. Who knows? But they defined it as this, and everybody uses it. Every electrician, every engineer, whatever. It's a convention. Okay, so if you just go with it, trust it, it's all good. Let's look at an example. A proton moves at that fast speed through a magnetic field of magnitude, I said magnitude, then I gave it a direction, but magnitude and direction, 0.8 Teslas down. Determine the magnitude and direction of the magnetic force experienced by that proton. Based on the force, predict what the motion of the proton will look like. Okay, we'll start with magnitude. So this is the information we know. I said theta is 90 degrees. Well, how do I know that? Well, the idea is that, imagine you're looking at this side view. So the speed is right, the B is down, and that looks like 90 degrees. Okay? And the other thing is, usually, unless you're told an angle, pretty much it's always down. Unless they're parallel to each other, it's 0 degrees, and we'll talk about that later. Okay? So the magnitude, just go ahead, plug in the numbers, you get a tiny, tiny force, but it's a tiny, tiny particle. It's just a proton, right? So it's a tiny, tiny force for a tiny, tiny particle. And remember, we don't include the negatives in the equation. Okay, when dealing with forces, we deal with only the magnitude. Okay. All right. So it's a proton, and we want to look at the directions. We're going to use our right hand. Our thumb follows the direction of the positive charge, so our thumb is going to point right. Our fingers follow the magnetic field, which is given as down. My palm then should be in the direction of the force. Right hand, it'll be into the page. Try it yourself if you don't believe me. And you'll be pointing into your hand, will be into the page, and so that's my magnetic force on my little proton. Okay? Now here's the thing. What will the motion look like if the velocity is right and the force is into the page? This means that force and velocities are at right angle to each other. Now think hard, back in the course, where did we see force perpendicular to velocity? Oh, circular motion. Probably just read down the page. So therefore, under these conditions, you end up with an object moving in a circle. Okay? And then I can ask you questions related to the circular motion just to put everything together. But I'm going to stop the video here and we'll do a part 2 in a minute.